So I'm really happy to say that today we have the last lecture, which will be given by Andrea in the framework of her course. But at the beginning of this lecture, I would like to inform you that our next semester, I mean fall semester, in the frame of the lecture will start on October. And we had some agreement with Leo Stormer, who is with us right now. And it is planned that he will give 3 or 4 lectures on some. Leo, could you please say something?
So the plan for the moment is that I will talk about generalized quadrangles and finite geometries with application to graph theory and coding theory. So problems in graph theory, which sometimes are solved via generalized quadrangles, and also some codes constructed via generalized quadrangles. So it will be finite geometry with some applications to graph theory, some applications to coding theory. Try to make the schedule, so I will be in contact with Elena. It will
be sure, of course. Yeah, right. Yeah, we will contact a little bit more, and then there will be some plan of these lectures, and of course we will put all information about the course on the web page, and then we will inform all our participants and in general all our friends who would like to join to this program. Thank you very much, Leo, for your
interest. Thanks for the invitation.
Yes, thank you very much. Yeah.
Okay, thank you again, Elena. Thank you.
Yes, thank you. Okay, I think that now we can start the last lecture by Andrea, and she is going to talk about applications. So the floor is yours.
Thank you. I will try to share a screen. Okay. Just a second view. Okay, it's fine. It's okay. Yeah, okay. Just a second. Good. Okay, so hello everyone. Thank you very much for attending this last part of my talk, and in general, thank you very much for participating in this whole group of lectures. So as Elena said, the last part of this mini course is called applications. So just to remind you, we had 2 lectures before. In the first one, I was speaking about construction of transitive combinatorial structure. And I showed you one of the methods for constructing combinatorial structures that have the property being transitive. The second lecture was about construction of non-transitive combinatorial structures. I show you how you can combine the method in the previous lecture and how you can obtain non-transitive combinatorial structures. And in this last part, I will show you how you can apply those methods that we were using in the first and in the second lectures with some extra new topics that I will define you to give some very useful applications. By applications, I mean applications on coding theory. So the plan for today's talk is this one. First of all, I will give you again basic definitions and some preliminaries. Then I will show you some references on the topics regarding codes constructed from SRGS and block designs. Then in the 2 parts, third and the fourth, I will show you how one can construct codes from various matrices that are connected with combinatorial structures. Then I will just quickly show you another application of the methods that I was speaking about to obtain application in permutation decoding, and in the last part I will show you some open problems and conclude my talks. Okay, so first of all, I will be speaking about codes. And in the point of that, we will give some basic definitions which are necessary for understanding. So we say that a code of length n over the alphabet q is actually any subset of q to the n. Elements of the code defined in this way are called code words. In this talk, and in the methods that I will show you, we will be interested just in linear codes. So what are linear codes? A code C is called a QRA linear code of dimension m if Q, our alphabet, is equal to the finite field FQ for a prime power Q, and C is actually m-dimensional subspace of a vector space fq to the n. If Q is equal to f2, then this code will be called binary. You will see in some examples, I will show you the examples also when the field is equal to f3, then this code is called ternary code. Then we have quaternary and etc. But here, in examples, I will show you, I think, just binary and ternary, but you can obtain on various finite fields. Okay, so what are the basic accompanying definitions that are related with codes? First of all, we have to define the Hamming distance between two words. So if you take two code words x and y in fq to the n, then we can define the number. What is this number? This number tells you what is the number of positions in which these code words differ. We can define the minimum distance of the code to be the minimum of all Hamming distances. Then we can define the weight of a code word, which is the number of positions that are non-zero. For linear codes, the minimum distance is equal to the minimum weight, so we can define the minimum distance or minimum weight to be the minimum of all weights of a code word x. So actually, when we are speaking here about QRA linear code with parameters n, k, d, we say that this is a QRA, okay, and with index q, we say that this is a QRA linear code with length n, dimension k, and minimum distance d. And it will be called NKDQ code. Linear NKD code can detect at most d-1 errors in one code word and correct at most this number of errors. Okay, so when we are speaking about linear codes can be linear codes with specific parameters can be we can say good. In what sense? So we can speak about best known or optimal linear codes. What does it mean? So if you have an NK linear code, this code is said to be a best known linear NK code if this code has the highest minimum weight among all known NK linear codes. So if you have particular NK linear codes, among all those NK linear codes, those that are really good are the best known linear codes that have the highest minimum weight among all known linear codes. We will say that a linear code with parameters NK is optimal linear code if the minimum weight of this code achieves the theoretical upper bound on a minimum weight of NK linear codes. And it will be near optimal if its minimum distance is at most 1 less than the largest possible value. Okay, so if you want to construct linear codes, specific linear codes, then it is always an idea and a hope that in this method or in this construction, you will obtain very nice codes. And by very nice, we mean that their minimum weight is near the weight that can be achieved by theoretical upper bound, or at least that it is the best known linear code. Okay, so in the application of linear codes and engineering and a lot of other areas, the codes that have a nice application have also nice properties. So one of the best known linear codes are those that have also the property of being self-orthogonal or self-dual. So when the code will be self-orthogonal or self-dual, so first of all, we have to say what is the dual code. The dual code is the and it is labeled with this. It is the orthogonal complement under the standard inner product. Actually, it is the set of all vectors from FQ to the N, such that the inner product with C gives you 0. We will say that a code is self-orthogonal if it is contained in its dual code, and it will be self-dual if equality is attained. It means that code is equal to the dual code. We can define the fact that two linear codes are isomorphic if one can be obtained from the other by permuting the coordinate positions. And automorphism of the code is isomorphism from C to C. We will say that two codes are equivalent if one of the codes can be obtained from the other by permuting the coordinates and permuting the symbols within one or more coordinate positions. Okay, so this is a majority and the most important things that we will need in start for following the basic of the methods that I will show you. Okay, so how there are many methods for constructing linear codes and for constructing linear codes with very nice properties. So a lot of people who are working in a field of linear codes and in this area are trying to prove existence of some special self-dual codes. They are trying to find new methods for constructing these nice codes, and it is a very interesting area to work on, since the application that is behind the construction of these codes is very wide. Okay, but I am interested in this talk in the codes that can arise from combinatorial structures. So in the history of this study, I wrote here two papers that I pointed out as the papers that are dealing with construction of linear codes that are spanned by adjacency matrices of strongly regular graphs. Nowadays, you can find many other papers, but I think that in these two, the construction of codes that are spanned by adjacency matrices of strongly regular graphs can find its beginning. So what is actually described here? Here is described how you can use adjacency matrices to obtain codes. How you just expand the linear code with the columns of adjacency matrices of strongly regular graphs, and you can obtain very nice codes. In these two papers, binary codes were studied. Also, if you take block designs as a combinatorial structures, you can spend and you can obtain codes in a way that you spend the space by incidence matrices of block designs. This is something that was also studied a lot. You can find in this book Designs and Their Codes by Asmus and Key in the details, very nice explained this procedure, but there are many other papers which are actually dealing with codes that could be constructed by incidence matrices of block designs, and here are just some of those that I point out here. Okay, so here we have codes spanned by adjacency matrices, and here we have codes spanned by incidence matrices. So in last lecture, I was speaking about orbit matrices of block designs, and I gave you a definition of an orbit matrix of a design. And actually, we were speaking about orbit matrices of strongly regular graphs. So, as I said in the last lecture, orbit matrices can be used in a way that I was speaking in the last Tuesday in order to construct new designs and in order, or strongly regular graphs, and in order to prove existence of combinatorial structures. But these orbit matrices can be also used in order to obtain linear codes with nice properties. One of the papers that started to use orbit matrices of designs to obtain codes is this paper written by Harada and Tonja, in which they gave a construction, a method for obtaining codes that have the property being self-orthogonal. Nowadays, this study of construction of codes from orbit matrices of designs and strongly regular graphs is developed further, and you can find it in also other papers. Okay, but today I am interested in showing you how we can extend some of these methods in a way that we want to use not incidence matrices of designs, not adjacency matrices of strongly regular graphs or orbit matrices, but we want to use some other matrices, integer matrices, and to construct codes, linear codes with nice properties. I will just remind you of a strongly regular graph. We introduced strongly regular graphs in each of the part of the lecture, but just to remind you, it is an incident structure having V vertices. All the vertices have the same degree. It is a regular graph, and has the property that if any two adjacent vertices are adjacent to lambda common vertices, and any two non-adjacent vertices are both adjacent to mu common vertices. One of the property that I think that I didn't remark so far is a very well-known remark, which says that the complement of strongly regular graph with parameters vk lambda mu is again strongly regular, and we know what are the properties, what are the parameters of this strongly regular graph. We know what is the regularity number and what are the lambda and mu. And this is not very difficult to prove. You just have to play a little bit with vertices, and you have almost immediately. Okay, so so far, when we were introducing strongly regular graphs, we were speaking about adjacency matrices of strongly regular graphs, which is actually showing you the adjacency relation between vertices in this graph. But today I am interested in 3 other matrices that can be that are connected with graphs. So let us define the first matrix. So let G be a graph with adjacency matrix A, having the rows and columns labeled by vertices V1 up to Vj. We can define Seidel adjacency matrix of this graph to be the matrix S defined with this number. So Seidel adjacency matrix is 0, -1, 1 matrix. The 0 will be in the position where Vi is equal to Vj. -1 will be on the position in which 2 vertices are adjacent. And 1 will be on the position when they are not adjacent. So actually, we have that Seidel adjacency matrix can be also defined with adjacency matrix. So if you have J to be all ones matrix, I, V times V identity matrix, and A adjacency, then Seidel matrix is equal to J minus I minus 2 times A. Seidel adjacency matrix is used very much in switching of graphs, and if you go to look up for some of the research and studies regarding Seidel adjacency matrix, you will always find some relation with the switching method. 2 other matrices that I am today interested in are called Laplacian and signless Laplacian matrix. If you take G to be a simple graph with adjacency matrix A, and if you put D to be diagonal matrix having the degrees of G on the diagonal, with the same vertex ordering as in adjacency matrix, then D minus A is Laplacian matrix of this simple graph G, and it is sometimes called the Laplacian or admittance matrix. Signless Laplacian matrix is defined to be, labeled with L among absolute brackets, which is equal to A plus D. These 2 matrices are called by Laplacian, which has some roots in engineering where Laplacian matrices are used. Okay, so what I am now interested to show you, I want to show you how you can use Seidel and both Laplacian matrices of strongly regular graphs in order to obtain codes having the properties to being self-orthogonal. I will show you actually, I will not go into details in this paper. You can find all the details, but I will show you how you can use these matrices. This is very useful. Why? Because there are, of course, plenty of strongly regular graphs, but for each strongly regular graph, now you can use Seidel and both Laplacian matrices, but not just Seidel and Laplacian matrices, but also orbit matrices. So far, orbit matrices were defined for block designs and strongly regular graphs, but not for some other integer matrices. So here actually we introduced the notion of orbit matrices of these certain integer matrices. Okay, so If you remember, for obtaining orbit matrices of block designs and strongly regular graphs, we needed an action. Of course, what is easy to do when you have an incident structure, then you have an automorphism group of an incident structure, and then you know that this automorphism group acts and gives you a partition, etc., that I was speaking last time. Here you have integer matrices. But if you want to define orbit matrices, then you also have you have to have action in order to build such orbit matrix. So how you can do that? Let M be n times n matrix. So a permutation automorphism of this matrix is a pair of n times m permutation matrices such that this equality holds. The set of all such pairs forms the permutation automorphism group of a matrix M, which is denoted by P out of M. Why P? Because this is, if we just write out of M, then it can be regarded as the full automorphism group of the structure, but it is permutation automorphism group of a structure. To remind you, automorphism of a graph G is permutation of the vertex set that preserves the edge set. It is very well known that an automorphism of out of G induces a permutation automorphism of adjacency matrix, which is of this form. And it easily follows that any automorphism of a strongly regular graph induces a permutation automorphism of its Seidel, Laplacian, and signless Laplacian matrices. And this was important to have, because if you now can define this permutation automorphism group and connected it with Seidel, Laplacian, and signless Laplacian matrices, then you can have an action. So how you now can define and orbit an orbit matrix of these integer matrices? So if you take G to be a permutation automorphism group of an integer matrix M and acting in T orbits on the set of rows and the set of columns. As last time, you can define G orbits on rows and columns by R1 up to RT and C1 up to CT, respectively. And you can put the sizes of orbits to write to rows to be capital omega I and columns to be omega I. And then, if you take Mij to be the submatrix of your starting matrix M, consisting of the rows belonging to the row orbit and the column belonging to the Cj. And if you denote by capital gamma ij and gamma ij the sum of some row and some column of this submatrix, then the sums of entries of any two rows or columns of submatrix Mij are equal. So the choice is arbitrary. It means that these numbers are well defined. And if you take a matrix with entries capital gamma ij, and if you take a matrix with gamma ij, you can define two matrices. One is called a row orbit matrix of integer matrix M with respect to group G, and the other, which is labeled by C, is called a column orbit matrix of matrix M with respect to the group G. Just to remind you, when we were speaking about incident structures, we were watching the G orbits on points and blocks. Here, this is more general. And with this definition is actually collecting the points and blocks as rows and columns or vertices of strongly regular graphs. Okay, so this is something what we introduced because we needed these matrices. Why? Because we saw that they have very, very nice properties in techniques for obtaining nice codes. Okay, so if you take graph G to be strongly regular, then if you denote by SL and with this label, you will have Seidel, Laplacian, and signless Laplacian matrices of graph G. What you can show? You can show that the elements of squared matrices are having these three entries. So for each of the matrix Seidel, Laplacian, and signless Laplacian matrices, they always have three different entries depending whether position is equal, whether vertices are adjacent or not. How you can see this? You can actually obtain this immediately, having the strongly regular graphs with these parameters and knowing the adjacency or non-adjacency of vertices. And this is something what actually in start helped us to see how quickly we can show and to obtain how we can obtain self-orthogonal codes. Why? Now you will see. Okay, just to write in short, I will introduce the little bit different notation. I will always use alpha, beta, and p, not gamma, because gamma is in our work always somehow related with the entry of the orbit matrix. So it will be alpha, beta, and p. And I will emphasize you whether the matrix M is Seidel, whether it is Laplacian or signless Laplacian. And when it is Seidel, alpha will be the one that it is, beta what is, and p what is. And when it is Laplacian, it will be k times k plus 1, etc. Just to note here and to remind you, M is symmetric matrix, so M square is actually equal to MM transpose. Okay. So now when we can say something about squared matrix and the entries of these three square matrices, then we can conclude something. This is something that that is very important. So let us see what this is. So if you take G to be a permutation automorphism group of the integer matrix M, it does not matter whether it is Seidel, Laplacian, or signless. I will denote it with M. It is with all three matrices it is working. And if you take R1 up to RT and C1 up to CT to be G orbits on the rows and columns of the matrix, then you have that this formula holds. So you just to remind you, gamma, capital gamma ij are the elements here, just to show you here. So are the elements in the row orbit matrices, and omegas are lengths of the orbits. Okay, but I need this result, which will be the crucial in the main theorem. But here I gave you just to show you that this formula is equal to this statement. What does it mean? You have Kronecker symbol multiplied with alpha. You have this element CIS times beta, and you have this times P. So alpha, don't forget that alpha, beta, and pi are actually the constants in our matrices. Okay, so why I needed this result? I needed this result in this very important theorem, which says, if you take G to be a permutation automorphism group of a matrix M, acting with T orbits that are all of the same length. So what you have a matrix, you take a permutation automorphism group of this integer matrix, which is Seidel Laplacian or signless Laplacian matrix of strongly regular graph. So always have in mind that this is not any integer matrix. It must be one of these three matrices. And this group acts in a way that it is producing T orbits on rows and columns, which are all of the same length. Okay, if you take R to be row orbit matrix of M with respect to G, and so you can build the row orbit matrix. If you take P to be a prime, which is dividing numbers alpha, beta, and P, then linear code that you can obtain by spanning with the orbit matrix of these matrices is self-orthogonal and have a length T. This is just a sketch of the proof, but I wanted to show you what is happening here. Very nice property. These are the same length, then everything is the same. You have that these sums are equal to this equation. So if you find a P to be a prime dividing alpha, beta, and P, what you will get? Actually, here you are multiplying the rows of an orbit matrices. So actually, if P is prime power dividing this number, in the field in which we are building linear code, it will be 0 modulo Q. So it means actually that you have self-orthogonal code. And this is very, very nice technique. So the main property is that you can obtain orbit matrix. You can have a permutation acting in a particular way. But because of the nature of these nice matrices, Seidel, Laplacian, and signless, you can obtain self-orthogonal codes. This theorem can be further obtained in a way and generalized in a way that this group does not have to act in all orbits of the same length. But if this is not the case, then you have omega j, which are the lengths of the G orbits on the columns, which are various numbers. And then you have a little bit different conditions. But the conditions are here. You also have some divisibility conditions. And if these divisibility conditions are satisfied, you have that your now part of submatrix of orbit matrix will give you self-orthogonal code. So in this way, when you have all orbits of the same length, then the whole orbit matrix will span you a self-orthogonal code. But in this case, when you don't have all orbits of the same length, you will have a submatrices that will submatrices of orbit matrices that will produce you self-orthogonal codes. If you don't have all lengths of the same weight, and if some of the lengths of orbits are equal to 0, Then these rows will be called fixed rows and fixed columns, but also using these parts of an orbit matrix, you can obtain self-orthogonal codes. So, and this is what is given in this corollary, but the main idea is actually this. You take strongly regular graph, you know the parameters of this strongly regular graph. So if you know the parameters of strongly regular graph, you know actually what are alpha, beta, and p for this particular graph and for this particular matrix. And then you can try to find a prime number that is dividing alpha, beta, and p in order to obtain self-orthogonal code. And then just, it is easy, you just applied these theorems depending how the group is how the group is acting, and you have self-orthogonal codes. I will show you a few examples. I will not go in details, but I will show you the examples, how you can use transitivity property. So it is known that a strongly regular graph with these parameters is having the full automorphism group U34 extended with Z4, but you know that the U34 group is acting transitively. So knowing this fact, you can easily construct that. You can use the method that I showed you in the first part. You have a group and you can construct this strongly regular graph. Okay, by constructing this strongly regular graph, you obtained its Seidel, Laplacian, and signless Laplacian matrices, and using these matrices and particular subgroups of the permutation automorphism group of these matrices, you can obtain orbit matrices. By obtaining orbit matrices, you can obtain some nice results. So here are some of the results that I have emphasized here. So here you can see the subgroups that were used in this action. You have, now you can see that these codes are ternary. So it means that the divisibility condition was satisfied when P was equal to 3. And here are linear codes, self-orthogonal linear codes constructed. Here you always have self-orthogonal codes. And here are the automorphism group of the codes. And these are those that are constructed from Seidel matrices. Why this one has a label? Because it is optimal. So these parameters, this minimum distance actually achieves the theoretical bound for this parameter set. Similar things, construction is here. When you take a strongly regular graph with these parameters, actually, this is the complement of the rank 3 graph with these parameters. And you know that U52 acts transitively on this graph. And again, now here we are interested in Laplacian matrices. So I must point out here that the divisibility condition for the P equal, here it goes for P equal to 3. But maybe for Seidel Laplacian, it does not follow because alpha, beta, and P are different in each of the matrices. So you have to be careful. Here are also very nice results that we obtain. What did I emphasize here? Here I emphasize the dual of the self-orthogonal code, which is actually near optimal. So the minimum distance is 1 less than those having theoretical bound. And here are the results for signless Laplacian matrices. Here you have the lot of stars. So this codes very nice. Here are binary codes, binary self-orthogonal codes, and obtained from strongly regular graphs on which the U-82 acts transitively. Okay, so I have to remark here that this construction that I've showed you actually gives you immediately another construction and shows you how you can play just a little bit with some properties of these matrices, and you can obtain even more range of strongly regular graphs that are satisfying divisibility condition property. So if you see, this expression was the most relevant for our theorem to be proved, but we may rewrite this equation in this way. So we can rewrite it in this sense, and now if we have the condition that P is dividing alpha minus P, a beta minus P and P, then you can have some parameters of strongly regular graphs that are satisfying this condition and will give you self-orthogonal codes. So this shows you how actually you have so many freedom in choosing strongly regular graphs. You have a lot of parameters satisfying this divisibility condition, and you can try to construct as many linear codes as you can. Okay, so this was the part that I wanted to show you how you can construct self-orthogonal linear codes using integer matrices that are not adjacency, that are not equal to adjacency matrices of strongly regular graph, but are Seidel, Laplacian, and signless. Now I wanted to show you how this idea of introducing the orbit matrix of an integer matrix also works for an Hadamard matrices. So first of all, I will define you an Hadamard matrix. An Hadamard matrix of order n is n times n plus minus 1 matrix with the property that if you multiply H with H transpose, you will have n times identity matrix of order n. They are very, very famous matrices, and it is very well known that Hadamard matrix of order n can exist only if n is equal to 1, 2, or congruent with 0 modulo 4. And Hadamard conjecture states that these necessary conditions are also sufficient, but since the discovery of Hadamard matrix of order 4 to 8, the smallest open case is n equal to 668. Okay, so don't be afraid of this so many texts. I will just explain you what I wanted to tell you here by main idea. So Hadamard matrices are matrices that are preserving a lot of nice properties. And what we found out? We found out that if you can define orbit matrix of Hadamard matrix, having in mind that this is plus minus 1 matrix, then you can have certain conditions in order to obtain self-orthogonal codes. It is a legal question why one should do that, because if you have Hadamard matrix, then to each Hadamard matrix you can associate incident structure. So actually, if you have incident structure, then you can obtain orbit matrices of incident structure, which is known. But if you don't go with these steps, and if you take Hadamard matrix as integer matrix, and if you can define orbit matrix of this integer matrix, then you have a wider range of automorphisms to use. And this was our main idea. We used similar thing. The idea is the same. You can define an automorphism of Hadamard matrix in the same way as for those previous integer matrices. What we had to show, we had to show that when you are using an automorphism of permutation automorphism group of Hadamard matrices, you have equally as many orbits on rows as on columns of the matrix H, and we were able to define an orbit matrix. In what way? In analog way as for orbit matrices of Seidel Laplacian and signless Laplacian matrices of strongly regular graphs. So if you take permutation automorphism group of Hadamard matrix acting in T orbits on the sets of rows and columns, then you can again define G orbits on rows and columns. You can again take submatrices of this matrix belonging to the row orbits and column orbits, and taking sums of taking sums of rows and columns of these submatrices, you will obtain row orbit matrices and column orbit matrices of Hadamard matrix with respect to the group G. So this is important. Row orbit matrices of Hadamard matrices, not of some incident structure. Because Hadamard matrices are nice in a way that have nice properties, we were able to prove the theorem, which is written in the similar manner as the one that I explain you in details. But the thing is, again, you take an Hadamard matrix, you take a permutation automorphism group of an Hadamard matrix, in this way having all orbits of the same length. You can build then the row orbit matrix of this Hadamard matrix. And if you have a divisibility condition in this sense that P is prime dividing N, then linear code that you obtained by spanning by matrix R, you will obtain self-orthogonal code of length T. Again, you don't have to have action with all orbits of the same length. You can have various lengths, but then you have a little bit different condition properties, but you will obtain again self-orthogonal codes. Okay, so I wanted to show you these methods because they are related with the properties and with the methods for obtaining incident structures that I was showing you in first two lectures that I gave. This last application that I wanted to show you has a title Permutation Decoding, and this is actually one application that is mostly detached with the first method that I showed you, in which was related with construction of transitive combinatorial structure. In this in this previous application, obtaining self-orthogonal codes, you are dealing with orbit matrices. Okay, you can have transitive structure, but then from this you obtain orbit matrices. So you need those methods for obtaining non-transitive objects. But this permutation decoding is very much close to the method for obtaining transitive structures. You will see why. So what actually this is? So just to remind you, the thing that I showed you in the first slide, an automorphism of a code is any permutation of the coordinate positions that maps code words to code words. If you take gamma to be a graph, and if you say that C is the code spanned by the adjacency matrix of gamma over the field F, then full automorphism group of the graph is subgroup of the full automorphism group of the code. This is something that is very important. Okay. So let's see what is actually permutation decoding. What we can do, any linear code is isomorphic to code having the generator matrix in so-called standard form. What is the standard form? It is the form in which you rewrite this generator matrix in a way IK and then A, and a check matrix is given with this form. And this is something that you can always do to any linear code. The first K coordinates are called information symbols, and the last n minus k coordinates are called the check symbols. Permutation decoding as a method, as a decoding method, was first developed by McWilliams in 1964, and it actually involves finding a set of automorphisms of a code, which is called a PD set. So PD set is actually a set of automorphisms of a code. Actually, it is a set of elements of this group. Okay. We can define it properly. So if C is a T error correcting code with information set E and check set C, then a PD set for this code is a set of automorphisms of C, which is such that every T set of coordinate positions is moved by at least one member of S into the check positions of the code C. The property of having a PD set is not invariant under isomorphism of a codes. Actually, it depends. It means that it depends on the choice of information set. This algorithm that I explained you, McWilliams in '64 introduced in these papers. And here is also very nice paper in which you can see for details of permutation decoding. So permutation decoding is an algorithm that is actually using PD sets. And it is more efficient the smaller the size of a PD set is. So what is actually the idea? You are entering in the full automorphism group of the code, and you are trying to find automorphisms in the set of whole automorphisms with the property of those sets being PD sets. And you are trying to have as smaller size of this set as you can. This is computationally not easy at all. Why? Because when you have large automorphism groups of the code, then there is a bigger probability that you will find nice PD sets, but then you are dealing with huge huge, with large computational problem. We know some theoretical bounds for PD sets, and they are due to Gordon. He gave in this paper the lower bound, which is called Gordon bound. So you know that if S is a PD set for NKD code, then for NKD code C that can correct T errors, and R is equal to N minus K, then you have this bound. Okay, so how you know that you have a good candidate for using this decoding algorithm? So all those linear codes with a large automorphism group are possibly good candidates. So you are actually trying to build linear codes with large automorphism groups. Why? Because it is a good, they have a good feeling that you will find PD sets inside. Why this is connected and why this application is connected with the lecture that I show you in first part. In first part, I show you the method for constructing transitive combinatorial structure. Those groups that we were starting to construct transitive structures, the one examples that I showed you are majority were simple groups with huge automorphism groups. So if you just take a look again on this property, if you have graph or incident structure with a huge automorphism group, which you will have if you obtain the method that I showed you, you are sure that your code, if you span a code with these matrices, adjacency matrix or incidence matrices, then you are sure that the full automorphism group of your code will be at least the size of the full automorphism group of the structure that you started, but it can be even bigger. So this is a good start for you to try to obtain candidates and to have sets that will satisfy the condition to be PD set. So in that sense, you can use the method that I show you in order to obtain PD sets. Some of the open problems that are regarding with this that I mentioned today is that construction of linear codes having nice properties. These nice properties, I mean on having self-orthogonal properties or even maybe self-dual properties, using matrices that are connected with graphs, as we did with Seidel Laplacian, sinus Laplacian. Study of PD sets obtained from graphs having large automorphism groups. This is something that is very much appreciated in the engineering world in a way that this set can produce you very nice decoding method. And of course, always development of new methods for obtaining some families of codes, some especially linear codes or some other codes. In these 3 parts of my lectures, I wanted to show you how one can use this nice area of finite groups, permutation groups, in order to combine finite groups with designs, with graphs, And here in the last part with linear codes, in order to obtain very nice, very nice examples. Designs and graphs are in some, not in somehow, they are definitely in some way arising from groups. So it is very nice to study this structure as much as we can. With this last part, I wanted to show you that these structures constructed in this particular ways can have applications also in some other parts in the coding theory and also in some engineering world. I would like to just show you one thing that I put here in open problems and conclusion. It is not a problem, but it has a word open. So in Rijeka, we have an open postdoctoral position in our discrete mathematics group. It is a group which is working in this field that I was speaking you about in these parts of lectures. So this is a position that lasts for 2 years, starting from the 1st of January 2022. And the more information, if some of the students who are here, or if you know any student that could be interested in the position, please forward the link in which you have more information about that. I would like to thank you all for participating in these 3 parts of my lectures. And the special thank goes to Elena. Thank you very much for inviting me to be in part of very nice lectures and to be part of this whole process of lecture. This is thank you and goodbye from Rijeka. Thank you.
Okay, Andrea, thank you very much. Yeah, thank you very much for this talk as well as for the course at all. And first of all, let me ask our participants: are there any questions to Andrea?
Yeah.
Yeah. Yes, Vladislav. Yeah.
Thank you very much for the very interesting lectures. And I would like to ask you,
Professor,
can you use these graphs to construct interesting code?
Yeah, you can. Yes, this is something that I'm working. This is a topic that I'm working on with my colleague Dejan Crnkovic, and yes, you can. This is work in progress. That's why I didn't put it here, but yes, you can, because the graphs have very nice properties that also are good for obtaining these families of codes. Yes. Yeah, we are soon finished, so we'll see.
Thank you very much.
Very nice. Are there any other questions to Andrea?
Andrea?
Yeah, Gary, please.
Professor.
In some of your tables, you gave the orders of the automorphism groups of linear codes, and they're really very big.
Yeah, they are huge.
Yes. Does that mean that you know what the automorphism groups are, or you just computed the orders?
Some of them we know. Well, some of them we couldn't compute. And for some of them are this huge, some of them are symmetric, but here no, I think here no. But here, for example, when we have smaller, then we know what is the structure of the group. But they were not, they were connected with the starting group.
Sure. Yeah.
Some of them. But for all of them, we couldn't get the structure, so we didn't wanted to emphasize some of them.
Okay, that would be interesting to know what some of these groups
What
are.
is?
Thank you.
Thank you, Professor.
Are there any other questions? Comments? Well, if not, then let us again thank Andrea. Thank you very much. Thank you. Well, it was great to have this mini course, and too many information, too many questions, open questions. And I'm sure that in a nearby future, we will get some answers. Even for today here in Rogla, we have 5 contributed talks, and all of them, I think almost all of them are joint work with you, right? Yeah.
I don't know if but a lot of them are joint work with
maybe, and
yes.
one is with Leo, I think, right? Yeah. Yeah.
Yes, it is Nina.
Yeah.
Nina is speaking. Yeah.
Right. Yeah.
It is.
Yeah.
It is. She is postdoc here in Rijeka. Yeah, my colleague also.
Yeah, good, very nice. So here in Roglo, we'll continue to listen some lectures on quads, and if it will be possible, then I will try to share these recording lectures with you, because actually it is very interesting to know what is going on in this area. So it is really real life, and just online we get information from our lectorium and from the school. Well, thank you very much. I would like to thank all participants of this lectorium, and now it will be something like a summer vacation for us in July, August, and September. And starting from October, we will get lectures by Leo Stormer, and as I said, that we will share this information with all our friends, so you are welcome to participate. Thank you very much, and take care, and well, be healthy. So I hope to see you somewhere soon. Okay, bye.
Thank you very much.
Thank
Thank you. Bye.
Bye. Take care.